Solve the system. All right, so we're going to try to apply the steps here listed to solve a system of equations with 3 variables and 3 unknowns. So we'll begin by copying down the first equation as it is, and the second equation as it is. From here, we will try to eliminate x. So I'm going to maybe multiply the top equation here by -3. This will ensure that the x's cancel out when I add the two equations together. So this should lead to -3x minus 3 times -y is going to give you plus 3y minus 3z minus 21. The second equation, left unchanged, is just 3x plus 2y minus 12z is equal to 11. If I add these together, the x's cancel out. I end up with 5y minus 15z is equal to -10. Okay, let's hang on to that equation. And we'll move on to step 2. We're going to take equation 1 and equation 3. So here's equation 1 again. X minus y plus z is equal to 7. Here's equation 3. 4x plus y minus 11z is equal to 18. So I'm going to multiply the top equation by -4, and that should eliminate x again. So we'd end up having what? If I move this down here, we'll have -4x plus 4y minus 4z is equal to -28. And then we'll have 4x plus y minus 11z is equal to 18. If I add this together, the 4's here cancel out the x's. Then we'll have 5y minus 15z is equal to -10. All right, now this equation turns out to be exactly the same as that equation in this example. That's not normal for that to happen, because if we tried to move to the third step here where we try to eliminate y using these two equations we just found, what's going to happen? Well, let's confirm what will happen. I'll have 5y minus 15z is equal to -10 over itself, basically. 5y minus 15z is equal to -10. So for example, if I try to eliminate y, I might multiply everything in the second equation by a -1, which would change the signs in the equation. And then I would add everything together. Well, that would cancel out, this would cancel out, and this would cancel out. We end up with 0 is equal to 0. Okay, so what this true statement means, that 0 equals to 0, is that essentially this system has an infinite number of solutions. That doesn't mean that everything is a solution, however. So in order to show what the solutions are, we have to give them a structure. There's going to be a whole bunch of solutions, an infinite number of them, but the infinite number of solutions will have a structure. It doesn't mean that anything you plug in will work. For example, if I said, well, let x be 1, y be 1, z be 1, that's not going to work, because then in the first equation, for example, you would see that that would give you 1 minus 1 plus 1, and that's not equal to 7, right? So just because there's an infinite number of solutions doesn't mean everything is a solution, right? So what we have to do is give a structure to the answers so that people can say, well, there's an infinite number of solutions, but what types of solutions or what form would they have? So what we're going to do this is we're going to say, okay, let z be equal to z. So z is z. That's a simple, obvious statement. If that's the case, then we can solve the equation we just had for y, assuming that z is like a constant or something we can plug a number in for, right? So let's go ahead and solve the system above for y. To do that, you're actually just going to take the 5y minus 15z equals to -10, and then just add the 15z to both sides. And that will give you 5y, the 15z's will cancel out on the left-hand side, and you end up with 15z minus 10. Then you divide everything by 5 here. And that will end up giving you the idea that y is equal to, well, 5 goes into 15 3 times, leaving you 3z, and 5 goes into -10 a -2 times. So now you have an answer for y. You had an answer for z before. The only thing left is to figure out what x would be then. So take any equation you want from the system. I'm going to take the first equation because it's probably simplest there. And remember, the first equation was x minus y plus z is equal to 7. And then substitute the things we just found for the other two variables. We said that we would use for y 3z minus 2, right? So remember, when we were looking at y before, we said that y would be equal to 3z minus 2. So in for y, I put 3z minus 2. For z, I'm just going to keep it as z. We said we'd make z, z. And then that should all equal to 7. So this is going to lead to the idea that x minus 3z, I'm just attributing in the negative here now, plus 2 plus z is equal to 7. Giving myself a little room to work here. That will lead to the idea that x, if we add negative 3z and positive z, we get minus 2z. And if we bring the 2 over here, it becomes negative 2, so it'll be equal to 7 minus 2. So we have x minus 2z is equal to 5. And then finally, if I bring the 2z over with a 5, I'll get the idea that x is equal to positive 2z plus 5. From here, we can form the solution to our system then. We're going to say that the solution set is going to be basically of the structure 2z plus 5 for x. The y coordinate, as we said before, would be determined by 3z minus 2, 3z minus 2. And lastly, we said that z would just be determined by your choice of z. So basically, in order to come up with a solution for the system here, you pick a z, and then once you've picked a z, you basically evaluate each of these other pieces, and you will come up with a point that works in that system above. Because you can pick any z you want, you have an infinite number of possible solutions here. However, again, as mentioned before, an infinite number of solutions does not mean that everything is a solution. The answer must be in the form that it fits this structure. So if you pick, for example, 0 for z, then your answer will be 5 for x, negative 2 for y, and 0 for z. If you let z be 1, then x would be 7, y would be 1, and z would be 1. So on and so forth.